Okay, welcome everyone. So now that we've considered a couple of examples where our vector spaces were a little more abstract, polynomial vector spaces and matrix vector spaces, let's take a look at some additional examples for these types of vector spaces. So now we're going to consider the vector space P2. Okay, so this is going to be the set of all polynomials that have degree 0, 1, or 2. And so following off of our previous example, we have a basis for this vector space because we're going to equip this set with the usual operations of addition and scalar multiplication, that a basis for this set would be 1t and t squared. This is probably the most natural basis that you might want to consider. So here's a set of three other polynomials in this vector space. So 2t squared plus 1, that certainly is a vector in this vector space. Then we have the quadratic vector t squared minus 1, and then I have the vector t plus 2. And I want to consider whether or not is this set a basis for the vector space P2, which we know does has some basis that has three elements. So we have three elements here. The question is, are these three vectors linearly independent from each other? And so they are going to be linearly independent from each other as long as when we look at this vector equation, which is weight C1 times vector V1, which now our vector V1 is this quadratic 2t squared plus 1, plus some other weight C2 times V2, which in our case is t squared minus 1, plus a third weight C3, which is a scalar, times our third vector in this set, which is t plus 2. And we want to know, is there some way that we can take a linear combination of these three vectors in the set and get the zero vector? And for this vector space P2, the zero vector would be the polynomial, the zero polynomial. So we want to see what sorts of solutions can we get from this equation that I've written above. And so we can group our terms using our operations that we've defined in this vector space. We group like terms. So I can rewrite this as a quadratic equation, which is 2c1 plus c2 times t squared plus c3 times t plus c1 minus c2. And I want this to equal 0. I'm curious, are there weights c1, c2, and c3 that are not all equal to 0, so that when I add these vectors together, I can wind up getting the zero vector? So that's why we're looking at this equation. And if we find that there is a non-trivial solution to this equation, then these vectors would not be a basis because they're linearly dependent. If we find that there is only a trivial solution, then we know that the vectors are linearly independent, and then they would be a basis for this vector space. So that's why this is the equation to take a look at. And what we can see is from this term right here, the linear term, if we're going to get a zero polynomial back, we see that C3 is going to have to be equal to 0. And similarly, if this constant term, which is C1 minus C2, if we're going to get the zero polynomial back, then the constant term should also be equal to 0. So that tells us that C1 is going to have to equal C2. And then finally, we can take a look at the coefficient in front of the t squared term, which is 2c1 plus c2. And then we can use our condition that c1 must equal c2 in order for the constant term to be 0. We plug that in to this equation over here. So in other words, I get 2c1 plus another c1, which is 3c1, and that has to equal 0 for us to get the zero polynomial back. So now this tells me that c1 has to equal 0 in order for this coefficient to be equal to 0. And therefore, since the only solution is the trivial solution, since we found that c1 has to equal 0, which means that c2 is 0, and we already know that c3 has to be 0. So the only solution to this vector equation is if we set c1, c2, and c3 all equal to 0. And so therefore, this set of three vectors that we started with is a linearly independent set of vectors. And moreover, that this set of vectors we have three vectors in here, which is the same number of vectors that we needed to get a basis for P2 using the standard basis t squared t and 1. So we have a set of vectors that has the same number of vectors as the standard basis that we previously found and is linearly independent with each other. Therefore, this set of three vectors does give us a basis for P2. Okay, let's take a look at another polynomial vector space example. So we're going to still consider our vector space to be P2, the vector space of all polynomials of at most degree 2 with the usual operations of addition and scalar multiplication. And now we have a set of three vectors. 2t squared plus t is the first vector, t plus 1 is the second vector, and 2t squared minus 1 is the third vector in this set. And we want to know, is this a basis for P2? So let's check the condition. Are these three vectors linearly independent from each other? And the answer here is a lot quicker. The answer is no, because we are able to express the third vector in this set, 2t squared minus 1, as a linear combination of two of the preceding vectors in the set. So I've got 2t squared minus 1, and I can write that as 2t squared plus t minus t plus 1. So in this case, the t's cancel out, and I've got 2t squared minus 1 left over. So here we've written this vector v3 as a linear combination of the previous two vectors, namely v3 is equal to 1 times v1 minus 1 times v2. And so since this set of three vectors is linearly dependent, without even worrying about do they span all of the set of degree 2 polynomials, it doesn't even matter, because we've already violated the condition that these vectors would need to be linearly independent in order to be a basis, and they are not. So this set is not a basis for P2. Okay, so let's take a look at one last example in this video. So now let's consider the vector space of all 2x2 matrices with the usual matrix addition and scalar multiplication operations. And we've looked at this vector space, and we identified kind of a standard basis for this vector space would be the set of these four matrices that I've written above, where each of these matrices has one non-zero entry that we set to be 1, and the other three entries are all 0, and we just make it so that each matrix in our basis has a 1 in the different positions. So that's all four of these matrices. So now let's consider a separate set of four matrices. So here I've got the matrix 1, 0 in the top row, 0, 0 in the second row. That's our first vector in this set. Our second vector is the matrix across the top row of 0, 1, and then across the bottom row, minus 1, 0. Vector 3 is the matrix that has a top row of 0, 0, and a bottom row of 0, 1. And the fourth and final vector in this set is the 2x2 matrix whose top row is 2, minus 4, and whose bottom row is 4, 0. And we want to know, okay, is this a basis for all 2x2 matrices? And it has the same number of vectors as the standard basis that we identified, but are these vectors, are these matrices linearly independent from each other? And again, the answer is no in this case, because notice this very last matrix in our set that has 2, minus 4 in the top row and 4, 0 in the bottom row, we can write this as 2 times one of the vectors in this set, namely the very first matrix that I have here, 1, 0 in the top row, 0, 0 in the bottom row, minus 4 times the second vector in this set, which happens to be the matrix that has a top row of 0, 1 and a bottom row of minus 1, 0. And so if we combine these vectors as our scalar multiplication and matrix addition are defined in this vector space, then we would get back the matrix 2, minus 4 in the top row, 4, 0 in the second row. So this last element in our set can be written as a linear combination of the previous two. Therefore, this set is not linearly independent. This is a linearly dependent set of matrices, so it is not going to be a basis for all 2 by 2 matrices because it violates the linearly independent requirement that we have for a basis.